All right, I'm ready to get started, please. I don't want to interrupt you guys, so I'll just wait. Thanks. So today we're going to start a lab, and this is a half-life lab. And so there's two different places you're going to be going to find the lab. You're going to go to the Zoom and other important class links. But then to record your data, you're actually going to record your data in a link that's in the stream. So I've got two different locations you kind of have to go. And I'll be sharing stuff too, but you definitely need to click the link that's to the stream, because that's where you're going to be sharing your data so that we can all see it. So we're doing a half-life lab today where we are going to be determining the half-life of an element called candium, which is your Skittles bag that you have. And so what you can do right now, if you're at home, hopefully you have the Skittles bag. If you're here, you have one. So just carefully open your Skittles bag onto your plate. Try not to let it touch the table. Try to keep it on your little plate. And we're not eating them yet, but we will be eating them later. And if you're at home and you've already eaten your Skittles or you can't find them, you need about 15 or 20 items that are double-sided, so a coin might work. All right. Hey, guys. That's a lot of talking for opening Skittles. All right. So let me see if I can share the right document. Yeah, here we go. So today we're doing this lab called, can you guys see it at home? No, it just disappeared. Okay, let me try again. This one. The half-life of candium. It's radioactive dating. And you don't have to pull up this version. If you just follow along, I'll kind of walk you through what you need to do. So let's just read the discussion just to kind of remind ourselves what we know about half-lives. Grady, tuck that nose in, please. Many people have heard the term half-life and know that it is related to radioactive elements. Half-life is defined as the time required for half of any given amount of a radioactive substance, which are the parent atoms, to decay into another substance, which we call the daughter atoms. Radioactive decay is a constant process where the unstable radioactive element breaks down to become a more stable element by releasing radioactive particles and radiation. In this lab, you will use Skittles to simulate how atoms radioactively decay and how rocks of different ages have different amounts of radioactive elements. So we're going to test radioactive elements. Oh, well, I read this background, sorry. In radiometric dating, different isotopes of elements are used depending on the predicted age of the igneous rocks. Potassium and argon dating is good for rocks 100,000 years old, since potassium-40 has a half-life of 1.3 billion years. Uranium and lead dating is used for the most ancient rocks, since uranium-238 has a half-life of 4.47 billion years. By comparing the percentage of an original element to the percentage of the decayed element, the age of a rock can be calculated. The ratio of the two atom types is a direct function of its age because when the rock was formed, it had all parent atoms and no daughter atoms. So for this procedure, we're going to walk through this step together. But what you need to do first is in the classroom stream, you click the link in the stream, and that's going to come up with a data table that you should be able to edit. All right. So in the data table that you've just pulled up from the stream, can you type your name in a row? And go ahead and type how many Skittles you're starting with. And don't be jealous if someone has one more than you. It was your luck. You chose the bag. So again, it's in the stream, and we're just typing our name and how many we're starting with. Keeping them on the paper towel because the paper towel is our plate. So for now, we're counting. All right. Have we all counted our Skittles? Yes. So now you're going to put your Skittles in a little cup. If you're at home, you can put them in your hand and shake them. So put them in your little cup. And we're going to shake them for about 7 seconds. Doesn't really matter. All right, pour them onto your plate gently so they don't go everywhere. All right, that's enough shaking. Pour them on your plate. So here's how it goes. The ones that have their S facing up are still radioactive. Separate your S ones from the ones that have the S facing down. So the ones that have the S facing up are still radioactive. How many have the S facing up? Put it under number 1 on your chart. The ones with the S facing up, count those and put them in your chart after half-life 1. You got to look carefully on those yellow ones in particular. That's an S. I usually use M&Ms because the M's last better than the S's, but I have allergies that make Skittles make more sense. Skittles were cheaper too when I was buying hundreds of them. All right, so now take only the S ones and put them back in your cup. The rest of them are stable and can be set aside. So take only the S ones, shake them up, dump them, and count how many S's are left. And keep doing that until all of your S's have disappeared. Only take the S's, shake those, see what you get. Yeah, I want you to keep filling in the chart. Yep. Keep going until they're not radioactive. The S ones are still radioactive. They're not safe to eat. And fill in your chart. Zoe, you had none of them decay at one point? Did you have none decay from one to the next? I'm looking at your data. You're at 144420. It looks like some people are having a bunch of ones that linger until it finally decays. Will it decay? Maybe, is it a double-sided S? The Yasus went real fast. Faster than normal. It's not a double-sided S, is it? Because then it would be messing with you. I'm sure that doesn't really happen. But I'm sure they only put S's on them one time. Okay. So I think you're all on the data table, and so am I. I'm on it on my other screen. So I'm watching your data. And most of us have eventually gotten to the point where it's 0, except for Rafe, who's having a really special time there. Looks like 11 times it has not been willing to decay. 12. Oh, okay. Should we just call it decayed? Yay! Okay. That was a lot of time. All right. Wow, some of you only had 14 and others had 16. Lucky people. Did anyone have 17? No, they're pretty consistent, I guess. All right. So you may eat your candy now. Just quickly pop them in your mouths and put your mask back on. Enjoy. Now that they are decayed and no longer radioactive, they are now safe for you to eat. We needed to get, huh? No, because you're not supposed to be touching food that you're giving other people. COVID rules. So, we've gotten them all to decay. And so take a look at this graph. You can see here that this is what your decayed parent atoms should have sort of looked like, right? We always have some exceptions. Some people's didn't always work perfectly, but for the most part, we were cutting in about half each time until we got to that final stubborn one. And what that means is that the ones that you set aside started off with 0, and it had a steady increase, and then you added a few less each time. And so these are kind of opposite graphs as the parents decay into what we call the daughter atoms. So tomorrow we're going to have a lab quiz based on our discussion today. So I want to go through these 5 questions, and then I'm going to show you something else, and all of this is relevant information that could be on tomorrow's lab quiz. So how much of a radioactive element becomes stable in a half-life? About half, right? Is it exactly half? No. Do you think in real life it's exactly half every single time? No, right? But about half each time. And you guys, for the most part, we are seeing patterns of it took about 4 or 5 for most people to be down, steps for most people to be down to 0, 4 or 5 half-lives. It took some people 3 half-lives, took some people 5. So it was approximately half each time, but not perfect. All right, here's a question based on Friday's notes. If you started with 100 Skittles instead of 15 or so, would the half-life change? What? What'd you say? I just couldn't hear you. Well, what does that mean? What is a half-life? Let's think about the definition of half-life. A half-life is the time it takes for half of them to decay. So if we started with more, would that adjust the time we should have been shaking each one? No. It would affect the number of times we shook, but each time for the half-life wouldn't change. It doesn't matter how much you start with. Because the half-life is the time it takes for half of them to decay. Now, the total time for all of it to decay would be adjusted, but that's not what they're asking. They're asking if we would adjust the half-life, which is the time it takes for half to go each time. And so that should have stayed the same. And then when we look at the data on the shared data table, how did yours compare to others? I'd say, unless you were Rafe with a weird shaped one that was throwing off his data, for the most part, everyone ended between 3 and 5 half-lives. So we're seeing some consistent data there. Now, this number 5 is about mathletes and mathematicians, because when math teachers teach half-lives, they teach it a little differently than I do, and they'd probably fight me on this. I don't fight back. That's why I don't want to be a politician. Half-lives, according to math, if you cut something in half and in half again and in half again and half again and half again and half again, you can keep going forever. You would never get to 0 according to math. You would get really, 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 really close to 0. But if we're talking about atoms, do you think it's possible that that last atom could decay? I think so, because you can't have a partial atom. And so we can actually get to having none of a radioactive material left over. That's probably what happened to the larger elements on the periodic table that we're able to make. They have really short half-lives. So no matter how much there was, if you cut it in half and half and half and half and half, and it's a really short time, we could get to the point where we have none of those atoms left naturally on Earth. Does that make sense to everybody? Now I want to show you something really cool. It might be on this page. Oh, where is it? Let's stop sharing that. I'll just Google it again. I'm Googling the words half-life decay chain and looking at images, and I'm going to pull some over. Let's start with this. That didn't work. Open it. All right. So this is the radium decay chain. And so this is radium-226. And so radium-226, if we had this radioactive element, it has a half-life of 1,600 years. That means every 1,600 years, approximately half of them have decayed. And when radium-226 decays, it does alpha decay into radon-222. Radon-222 has a half-life of 3.82 days. And then it does alpha decay into polonium-218, which has a half-life of 3.05 minutes, which does alpha decay into lead-214, which has a half-life of 26.8 minutes. So every 26.8 minutes, half of the lead that is made turns into, by beta decay, bismuth-214, which has a half-life of 19.7 minutes. And then this turns into polonium-214, which has a half-life of 0.16 milliseconds, which does alpha decay to make lead-210, which has a half-life of 22 years. So once you get to this stage, every 22 years, half of it disappears. And it does beta decay to bismuth-210, which has a half-life of 5 days, which beta decays into polonium-210, which has a half-life of 138 days. And then eventually that does alpha decay to make lead-206, which is stable. This is just one example of if you have one radioactive element, all the steps that it takes to get to stable. Because what we've been learning so far is we've talked about nuclear decay equations and things like that, and I said it decays to this. And I didn't really mention the fact that, and then it doesn't stay there. It decays into something else and something else and something else. And so most radioactive elements have these long chains. And so every 1,600 years, about half of this is turned into this, and then so on and so forth. But it's a really long step to get to stable. And neither of these are showing gamma, but remember how gamma radiation can come with alpha and beta? So maybe not all, but some of these steps are also releasing gamma radiation along the way. The other thing for us to consider, we're starting here with radium-226, and its half-life is 1,600 years. So do they all wait until 1,600 years have passed and then they decay? Or do they decay whenever they feel like it during that 1,600 years? Half of them do. The second option, right? So any time during those 1,600 years, at least half of them are decaying, or approximately half of them are decaying. And so it's possible that this stage could happen faster. In 1,600 years, that's how long it takes for half of them to decay, but maybe in the first year, 2 of them have, and then in the second year, a few more have. And so these steps are always going. You never know where you are in the stage, but basically all of our radioactive elements are in a path towards decaying with alpha or beta until they eventually get to a stable version of an element. Somebody asked me last period, oh, let me show you uranium-238, because that's a really interesting one. Let me open that one. Interesting for a few reasons. Oh, here it is. All right. So here's uranium-238. I'm going to make it a little bigger. And so this has a little key here. A stands for years, D is days, H is hours, minutes, and seconds. So uranium-238 has a half-life of 4,500,000,000 years. So every 4,500,000,000 years, half of uranium-238 has decayed. By the way, we think our sun is about 4.5 billion years old. So that means we think that our Earth at the oldest would be 4.5 billion years old or younger, because it had to have been gravitationally attracted to our sun. And so we've had maybe one half-life of uranium on Earth, which means that the amount of uranium on Earth right now is only half of what it was when our Earth formed. So there's still a lot of uranium left to go. So it has a long half-life. And then when the uranium atoms, which remember, it doesn't take them all 4.5 billion years to go, when they alpha decay, they make thorium-234, which has a relatively quick turnaround of only 24.1 days for each half-life. And then protactinium-234 is 1.17 minutes. And then it makes uranium-234, which is 240,000 years. And then thorium-230, which is 770,000 years. And then radium is only 1,600 years, and this is the step we just saw with radium. So radium-226, one of the ways it happens is from the decay of uranium-238. It's just one of those elements in that process, in that step. And so remember, it only is telling you alpha or beta. It's not showing you if and when gamma is being released, and it certainly is. In a series this much, gamma is going to be released in a lot of these reactions. And so we know there's radioactivity around us. We know that it's constantly happening and there's radioactive elements. We cannot stop that. There's new ones forming, and they might form with a long half-life, which means we're safer. We're less likely to get the radiation from that. And they might form something that's a shorter half-life where we're more likely to get radiated from that because it's going to happen at a faster rate. It just sort of depends. But what's important to realize is that they don't just go from radioactive to stable. You can have a long chain to get there. And that's where nuclear weapons are a really dangerous thing. Because besides releasing uranium-235, which we could look up its decay chain if we wanted to, but besides releasing uranium-235 into the environment, it's also, remember, uranium-235 is undergoing fission, so it's making all those other elements. And any and all of those elements can be radioactive as well. And then you're starting all these new chains that are released into the environment. And there might not be as long. Bigger elements tend to have longer chains, but it could still be a lot of steps in the process before you reach a stable element. Any questions about this? Okay. I did forget to ask you all at the beginning of class. I owe you 2 retakes this week that I'll assign later today. Retakes for balancing equations quiz for anyone who wants to take that, and also retakes for the nuclear equations quiz, which was Friday's quiz. If anyone hasn't taken Friday's quiz, now is an excellent time to go ahead and take it the first time so you know if you need a retake. And if you missed class or didn't finish in class and you couldn't find the equations are in that Zoom and other important links document. I use that document every single day. And so you can find the equations you need to do the quiz by clicking the Zoom and other important links document. So is there anyone in here or at home, you can communicate with me if you want to retake the balancing equations quiz or the nuclear decay quiz. I will assign it to everyone who failed it or hasn't taken it. Hi? Which one? Okay. So I will assign that later today. Okay. And I will include with them a short little video of me explaining it. So again, if you want a little refresher, if that will help you, you only get 1 retake, so it's always good to watch those videos. The other thing I wanted to remind everybody of, or let you know, just kind of know where we're at, because we're at the end of the year basically. So tomorrow we are going to do practice calculating half-lives based on the notes we took on Friday. So tomorrow we'll do tomorrow we'll start with the lab quiz on today's lab. And then we will do a practice worksheet and check our answers for calculating half-lives. Wednesday is your second day of the test grade to do research on nuclear radiation in your life. And you got to pick one of those topics and write those that research. And then the following Wednesday is when your Flipgrid is due. Basically, the Flipgrid, guys, is just you telling me what you learned and something that surprised you. Because in the world of online learning, I don't want you just copying and pasting someone else's answers. I want you to actually have learned something. And so the Flipgrid is just forcing you to have actually read what you're submitting and turning in. Sound fair? So that's 20 points in the test category. Then on Thursday and Friday of this week, we are going to be doing review, because on Monday, June 14th, I'm going to assign our last test. It is not a final exam, and I want to be clear about that. A final exam covers everything we've learned all semester. This is a last test. And it's going to be about balancing equations and the nuclear chemistry that we've learned. That's it. And you can take that test anytime during the week. And if you've turned that in and you've turned in your nuclear research assignment as well, you are done early for the semester. And if you do have missing assignments, the last moment I will take them is 3 p.m. on June 18th. And if you turn it in at 3:01, too bad, so sad. She's been nagging you for weeks. Get it together, people. Questions? All right. I'm done for today. I'll see you Zoomers tomorrow when we do our practice calculations. For those of you who are in here, if you have any missing assignments that you could be working on now, please do. Please, or work on your nuclear research for a little bit.